Any questions or problems crop up? No? Okay. We're gonna cover material for exam 4, I believe, chapter 6, which is thermal chemistry. And handouts for you guys at home. The usual PowerPoints, review document, worked problems, and a chapter 6 crossword puzzle, plus the lab for next week. I'm handing out in class today is on thermal chemistry. We're going to do a calorimetry lab where we use, well, I got a picture of it in the lecture. We'll show it to you when we get there. And that's it. So let's talk about thermochemistry. Let's see, I'm going to shrink that down a little bit. Get it out of my way. So the word thermochemistry ought to be self-explanatory. I've been doing chemistry now since the beginning of the semester, and now we're going to talk about the heat relationships in chemical processes. Just as an indication of where we're going, we will discuss topics like thermodynamics and energy budgets, things like that. But the useful part of thermochemistry is determining how much energy is either consumed or generated in a chemical process. And we can quantify that based upon what we've learned so far about stoichiometry. Okay, energy. I remember in grade school getting a definition of energy. Capacity to do work. Now, since we've added not just the capacity to do work, but to produce heat. And the reason for that is we've got to account for all the energy transfers that occur in any process, whether it's chemical or physical. And that's based upon the law of conservation of energy. In other words, energy cannot be created or destroyed. It can only be converted from one form to the other. And that is another way of stating the first law of thermodynamics. The total energy of the universe is constant. In other words, any changes in the energy content of the universe equal to 0. In other words, the universe, according to this theory, the universe has the same amount of energy it had from its beginning till now. It's just changed forms. That's another way of stating it. And for our purposes, there are very few, and I can't think of any offhand right now, chemical or physical processes that don't involve some transfer of energy when the process occurs. All right. We can divide energy into 2 categories. And remember, it's like I always say, nature just does what it does, and we try to explain it. So this is one of the ways we organize energy: potential energy versus kinetic energy. Yeah. Potential versus, is that right? Yeah. Okay. Potential energy versus kinetic energy. We're going to start with potential energy. Potential energy is simply energy that is not being used at the present time. Then that's why we call it potential, right? It's sitting there just waiting for us to do something with it. We can also subdivide that into energy based upon position. And what we mean by that is position in a gravitational field. In other words, I have a certain amount of potential energy right now at the surface of the earth because the earth's pulling on me. And the only reason I'm not giving up that energy is because I've got solid ground under my feet. If I were, say, to climb on top of the building, I'd have to expend energy to get up there. And then I'd get all that energy back by just jumping off the building. Well, I wouldn't get it back until I hit the ground, of course. But all that energy would be returned. The position, my relative position in that gravitational field determines the amount of energy that I have available and my mass. So my mass and the height above the center of that object determines my positional potential energy. The other type is due to composition. And compositional potential energy covers a much broader swath of that type of energy. It can either be chemical energy, in which case we're actually storing energy in chemical bonds, like say nitroglycerin. So when nitroglycerin comes apart, all that energy is released. Electrostatic attraction. So if I have or repulsion for that matter. It's kind of like it's similar to, but not exactly the same as magnetic. So if I have two magnets and they're north to south pole and I try to pull them apart, you'll feel a resistance, and it takes energy to get them apart. So I'm storing energy in that field between them. Or if they're north to north or south to south and you're trying to push them together, you got to add energy to it to get them together, and that energy is stored. And you know, if you turn them loose, they'll go that. Or if you've got one of these really strong rare earth magnets and you get too close to a metallic surface and your finger happens to be in the way, it's a pretty strong pinch as that energy is being released and part of it goes into your finger. There's elastic potential energy, such as in rubber bands. I remember as a kid, we used to get these balsam airplanes with little propellers on them, and they had a long rubber band underneath. And you just wind up that rubber band, then you can turn it loose, and that energy would be released. That elastic energy you stored up in the band would be released in the propeller, and the plane would fly off. It would usually curve if you didn't set it right, because that's a torque effect. Anyway, you can store energy in magnetic fields. You can store energy in nuclear, in the nucleus of an atom. There's stored energy. And we get some of that energy back when we allow, say, U-235 to spontaneously break apart. Right? So you can either get a bomb or you can get energy for peaceful purposes. And then there's thermal potential energy, and that is based simply upon the temperature. Temperature differences between two things allows for storage of thermal energy. And the way you get it back is you transfer that energy from the high temperature to the low temperature and have something in between to extract that energy on its way. So that's what we do under the hood of our automobiles. All right, so that's potential energy, either positional or compositional. Now, if the object happens to be moving, then you've got kinetic energy. And kinetic energy can easily be calculated for any object if we know its mass and how fast it's moving. Right? Its mass times its velocity squared, and take 1/2 of that, and you've got kinetic energy. This also refers to, it's kind of a bridge between these two, because we said thermal energy can be potential, but thermal energy is also kinetic because those molecules are moving. So there's kind of a bridge here. Maybe we ought to put thermal in between. We can talk about thermal in terms of potential or kinetic energy. So when we talk about positional potential energy, how can we, there's a a transition that can occur. If we have, say, this ball A is at that level and it's held in place by whatever mechanism you choose, then it has potential energy due to its height. If you turn it loose, then it's going to drop to a lower level in that gravitational field and generate motion. And now we got kinetic energy. So there's a balance between potential and kinetic energy in this process. Now, if we do that, and it happens to strike the ball B, it could transfer some of that energy to B, right? And if A stops where B is, then B takes off with the energy that A used to have. And that's what the next slide shows. The problem that this slide illustrates is that B doesn't go back up to the same level that A was. Well, if we abide by the conservation of energy, then we have to account for all the energy wherever it went. First, potential energy turned into kinetic energy on the drop, and it transferred that energy, and we're saying this collision was completely elastic. So A stopped, gave all of its energy to B, and B took off with its kinetic energy. And now it's rolling up the hill and converting that kinetic energy into potential energy again. But it didn't get as high. So where did that energy go? It went to friction. We converted it into heat. All right. So let's pause for a moment and talk about the difference between temperature and heat. I think I've mentioned in this class that temperature is an intensive property. In other words, if you have an object that is equilibrated with, say, a source that's putting heat into it, like we put a steel ball into boiling water. Eventually, the steel ball will come to the same temperature as the water. And the temperature is an expression of the average kinetic energy of all the molecules in the water and the steel ball. So it's an intensive property. It doesn't matter whether you're looking at the steel ball, you're looking at a thimble full of water, or the whole thing of water. It's all the same temperature. Right? So that's an intensive property. Heat, on the other hand, is an extensive property. In other words, it does matter how much you have. Also, we measure temperature with devices that give us an indication of that potential energy, but we can only measure heat by transfer. In other words, heat always flows from higher temperature to lower temperature. So we have to measure the difference, the movement of that heat some way, and we're going to do that later. We have to measure the transfer of energy as heat between two different temperatures. If you put two objects together with the same temperature, you get no heat transfer at all, theoretically. So that's the major difference between temperature and heat. All right. Now, I want to introduce another concept. Well, we use the words in the beginning. Energy is the potential to do work or create heat. And if we're talking about work, in physics, we have a formula for work, and work is defined as a force times a distance. In other words, when you apply a force to something and it moves through a distance, you've done a certain amount of work. So the illustration I usually use is I push on this board, I'm applying a force to that board, but it's not moving. So I'm not doing any work. But I'm still expending energy, so the energy's got to go somewhere. So the energy actually goes into causing the temperature to rise. I'm transferring energy into that board as heat. Right? It's not doing any work. So the energy's got to go somewhere. So there's heat being generated in my muscles, and there's heat being transferred and created in that space where I'm pushing. But if the thing moves under that force, we've done work. Now, here's another concept that might seem strange to you. I sort of alluded to it in the past. State versus path. Energy, this delta E, any change in energy is a state function. I should put it over here. What that means is it doesn't matter how it got there. It doesn't, the history or the future of that energy doesn't matter. It only matters what is it right now. That's a state function. A path function, on the other hand, depends on how it got there. So energy is a state function. Work and heat are not. Work and heat are path functions. Okay. There's another one. I might as well add it in here. We're going to talk about it later, called enthalpy. So these two are state functions. We use a symbol for heat transfer, Q, and heat and work. Those are both path functions. So how would I illustrate that? If I go from Charleston to Beckley, I've increased my elevation and my positional potential energy from, let's see, what is it in Charleston, about 700 feet? Or is it closer to 500? It's in that neighborhood, elevation. And up here, it's about 2,500 or 2,400. So I've essentially increased my height above the center of the earth by about 2,000 feet. And the energy that I've added to my position is this change in energy. And it doesn't matter how I got there. Nowadays, you get there on the turnpike. Right? So it's fairly efficient, quick. But in the old days, before I got here, people tell me that even before the turnpike, the only way you could get from Charleston to here was go the back roads and just wind your way around. So that requires a different amount of work. So the work required to get from Charleston to here in the past was much more. You had to, a force applied through a distance is much more than it is now. That's what we mean by a path function versus a state function. Let's see, somebody dinged in. Let me see who it is. Tucker. Must have been somebody going out, coming back in. That's okay. It happens. All right. So hold that thought. We're going to come back to it. Both work and this state versus path function. But now I want to introduce another idea. When we are discussing energy transfers, we need to define where the energy is moving. And we do that with this neat little trick. We say, okay, I'm going to define this as my system. And it could be anything. Whatever it takes to solve the problem. And then everything else is surroundings. So system and surroundings technique is just a way to solve problems. And the way it's set up now is the system has this region of space identified for it, and the surroundings is the rest of the universe. But that doesn't help us solve problems usually, because we can't account for the whole rest of the universe. So what we tend to do is we limit the extent of the surroundings. So now we're saying the surroundings are here, and this is an isolated system surroundings. Nothing gets through that boundary from the universe. Okay, now in terms of the system, we can define the system and its boundary here between system and surroundings. We can say it's either open, right, where energy and matter can cross that boundary. Right? And we do have examples of that, which take too long to talk about it now. Or we can say matter cannot cross. Say matter can't get in or out, but energy can. We can transfer heat, light, whatever the energy form we choose. The other possibility is isolated. Just like this is isolated, we can also say this is isolated. Now, nothing crosses that boundary. The best example for us is now when we have an isolated system, we're talking about our calorimetry cups. When we do our experiments next week, we're going to have styrofoam cups, 2 of them slapped together, and that's our isolated system. Okay. Get a drink while you guys are writing. All right. So, in terms of chemistry, once we define what our system is, we can say which way is the energy moving. If we say it's not isolated, let's just say, for our purposes, that the system is closed. So we have a closed system. That means only energy can transfer. If energy goes in, everything is in terms of the system when we define what's happening. We say in terms of the system. So if energy is going in, or let's be more specific. Let's say we're just transferring heat. If heat's going in, then we're adding heat to the system, and the sign on our Q value will be positive. If heat's leaving the system, then our Q is negative. Okay. And we say when it goes in, this is endothermic. Can you spell endothermic? And when it leaves, this is exothermic. So defining the system relative to the surroundings allows us to say that our process is either endothermic or exothermic. If it's endothermic, it has to absorb heat from the surroundings, obviously. So the heat that moves from the surroundings to the system, we add this much heat to the system, the surroundings have lost that much heat. Right? We can't create or destroy, so we have to account for it. It's like a budget. All right. So let's take an example and see if we've got this concept in mind. Freezing of water. Is it an endothermic or an exothermic process? Well, we have to define our system first. So our system is the water. So we have water here, right? Some whatever. So if it freezes, which way is the heat moving? This has to get colder, right? So it has to lose heat. So it would be an exothermic process. The freezing of water is exothermic. We define our system, we define the surroundings, we say which way is the heat flowing, and it's an exothermic process. That may seem counterintuitive because when you grab hold of ice, it's cold. But when you grab hold of ice, you're going the other direction. You grab hold of ice, your hand is the surroundings. So the energy is moving from your hand into the ice. That would be endothermic. But when we got water and we're freezing it, it's the other way. All right. So for these examples, and I already talked about this one, the first one, the underlined parts of the statement define the system. So your hand is the system in part A. It gets cold when you touch ice. So if your hand is the system and it loses heat to the ice, the surroundings, your hand is the system, that's an exothermic process. Your hand is losing heat. Ice gets warmer when you touch it. Now it flips around. Now it's endothermic. It's all relative to what we're defining as the system. Water boils in a kettle being heated. So the water in the kettle is our system and it boils. We have to add heat to it. That's endothermic. Water vapor condenses on a cold pipe, goes from a gas to a liquid. It has to lose heat, doesn't it? Okay, so the water vapor loses heat, it's exothermic, and condenses on the pipe. And then ice cream melts, of course, is endothermic. We have to add heat to the ice cream to make it melt. Okay, next. I better leave that there just in case. All right, for each of the following ones, we are going to have to define, there are two of them. We have to define what the system is in order to answer the question. And when you have a chemical process going on, one of the best ways to define what is your system is if you can write the balanced equation. If you write the balanced equation, that tells you what the system is. So this first one, methane is burning in the Bunsen burner, natural gas. So that equation tells us that methane, gas plus oxygen from the air, yields carbon dioxide and water vapor. Okay, so if we were to balance that one, let's see, can I remember how to do that? Let's see, 2 here. 2, that's 4, 2 here. I think that's balanced. That tells us that the gas and the oxygen mixture is our system. And as it burns, as it combusts, it releases heat. So if the system is releasing heat, that's exothermic. Okay. Now this one's not this is a physical process. Water drops on your skin and evaporates. So we have to decide, all right, which one is the system? If we say the water that drops on your skin is the system, then it would be endothermic to make it evaporate. Okay, and I think that's what we're getting at. Like I said before, we define these terms however it best solves a problem. Okay, hydrogen gas and oxygen gas react violently to form water. Okay, this question, I'm going to erase this. I can draw it again later. So if we've got hydrogen gas and oxygen gas, form water. Let's see, does it say? It just says form water. So let's say it's under standard conditions, so we get a liquid. And to balance it, we need 2 here and 2 here. Okay, which is lower in energy? First of all, what type of process is it? You get a lot of heat from this. It's exothermic, right? It's exothermic. Okay. Where did that heat come from? It's from potential energy. It's from the bonds. we break bonds here and we form bonds over here. And the difference between the two yields energy. So the bonds that we form over here must be at lower energy than the bonds we broke. Another way to look at it is, if it's exothermic, we know it's exothermic, then put the heat term in. The heat term would be over here as a product, right? So that tells us that energy was stored in the bonds over here. So these are higher energy bonds than there. There's more energy on this side than there is on that side in the bonding. Let's see. Which is lower in energy? This is lower in energy. And that's typically what drives chemical reactions. A lower energy means more stable, and chemical processes tend towards stability. So we're going this way spontaneously, actually, because these are a higher energy level than the water is. Okay. All right. Now, we'll say a couple of words about thermodynamics. We're not going to get into it really deep. Partly because we don't have time. And also because you don't need to know details about thermodynamics in order to solve problems in this course. And the other reason is one that I'm not competent. In order to really discuss thermodynamics in detail, you need to approach it from the math, from calculus. So we're just going to skim across the surface and get the ideas from it that will help us solve problems. So thermodynamics is the study of energy and interconversions. And these can be chemical or physical. So we've already talked about the law of conservation of energy. That's the first law of thermodynamics. So we got the first law, which is conservation of energy. Oh, we're not going to do the other laws? Okay. Well, there are actually 4 laws. I'll save it till later. Maybe pique your interest. It won't come out in this chapter. We'll get to it later. In fact, I think we don't get to the other laws until second semester. So here's another concept that we use to help us understand thermal processes. The concept of internal energy. Internal energy, or E, internal energy, references the system, and it's the sum of all the energies that can be accounted for in the system, both potential energy and kinetic energy, all of them together. And this, we're talking about the particles. In other words, is there potential energy due to position? Is there potential energy due to composition? Kinetic energy due to motion of any kind? And even though we define the term that way, the only way to measure it is in terms of change. How does the internal energy change? And that change can be accounted for by 2 other terms, our heat term and our work term. So any change in internal energy of our system can be accounted for by any heat that moves in or moves out, and any work that the system does on its surroundings, or that the surroundings happens to do on the system. And the sign convention is the same. If the system is doing work on its surroundings, it's losing work, so it's negative. If the surroundings are doing work on the system, then it's positive. Usually, and especially for our purposes, work is in terms of a change in pressure and or pressure or volume. And we're basically talking about gases there. All right. So just as a reminder, any of these quantities, measurement quantities, will have three parts to the measurement. One is the magnitude, the number. The other is the units. What are the units of measure? And energy units are usually in terms of joules. That's the SI unit for energy. But we have others that sort of creep in from the sides. Talk about those too. And the lastly is the sign. We have to have a sign on that energy in order to say which way is that energy moving. Is it going into the system? Is it coming out of the system? All right. So I'm not going to spend a lot of time on this slide because it just illustrates what I've already shown you. If energy leaves the system, then it's exothermic and the sign is negative. And if energy is being added to the system, and in this way, energy can have a positive or negative sign also, right? These can be positive or negative here, positive, negative, and energy, internal energy can be positive or negative also. And it depends on the balance between heat and work. So, for instance, if our system is, if we're adding heat to the system, is positive, right? But if at the same time the system is doing work on the surroundings, that's negative. So the sign of this one depends on which one's bigger. Right? If it's getting more heat than it's doing work, then we're adding to its internal energy. But if it's the other way around, then we're losing internal energy and it's negative. Right? We're going to do an exercise in a minute that'll illustrate that a little further. All right, we talked about this already. Oh, Professor Dave. We got time to listen to Professor Dave? I suppose. Let's see what he has.
Hey guys, it's Professor Dave. Let's talk about thermochemistry.
He knows a lot about the science stuff. Professor Dave explains.
Thermochemistry is the branch of thermodynamics that deals with the heat absorbed or produced by a chemical reaction. A reaction can either be exothermic, one that releases energy, or endothermic, one that absorbs energy. This change in energy is represented by delta H, or the change in enthalpy for the reaction. For our purposes, we can think of the change in enthalpy as being the change in energy for the reaction, or the energy stored in all the bonds of the products minus the energy stored in all the bonds of the reactants. If there is more energy in the products, delta H will be positive, meaning the additional energy had to be provided, making it an endothermic reaction. If there is less energy in the products, then that additional energy was released, making it an exothermic reaction. Energy, which is the capacity to do work, can have many forms, like mechanical, electrical, chemical, heat, and so forth. And besides quantum mechanical exceptions, energy is conserved. That means it can change forms, like heat energy that evolves when the chemical energy in a broken bond is released. But it won't be created or destroyed. Heat, represented by the letter Q, is a trickier thing to define. But a good way to put it is that heat is the energy that flows between a system and its surroundings due to a difference in temperature. Heat will always flow spontaneously from an area of high temperature to an area of low temperature. For a system, Q will be positive if heat is being absorbed by the system, and it will be negative if heat is being released by the system. When temperature and pressure are constant, Q equals delta H, the change in enthalpy. When we discuss thermochemistry, we will discuss energies in terms of joules or kilojoules. Another common unit used by chemists is the calorie, which is equal to 4.184 joules. 1 calorie is the amount of energy needed to raise the temperature of 1 gram of water by 1 degree Celsius. This is not to be confused with the food calorie, which is calorie with a capital C. This is actually equal to a kilocalorie, or 1,000 calories, also abbreviated as kcal. A thermochemical equation reports the change in enthalpy for a given reaction in stoichiometric terms. Here, the delta H listed is specific to the molar quantities given by the balanced equation. So if the number of moles of each substance as given were to react, the change in enthalpy would be as listed. To find the enthalpy change for a specific amount of material, just do some stoichiometry. If twice as many moles of material as are listed were to react, then the enthalpy change would also be twice as much as listed. Let's check comprehension. Thanks for watching, guys. Subscribe to my channel for more tutorials, and as always, feel free to email me, ProfessorDaveExplains@gmail.com.
He introduced some ideas here that I'm going to have to talk about in more detail to get some understanding out of. But let's go back to the idea of internal energy is equal to Q plus W. Work for a gas, we're going to equate, because gases, when we have a gas in a cylinder like this, so there's gas in that cylinder and a force is being applied, then that force moves through a distance and a certain amount of work has been done on this system. Okay, that's given. Force times distance. So if we move it down, say, from there to here, then this is the distance. And amount of work has been done on the system, that means the work is positive. Okay. But very often we measure not force and distance in terms of this moving piston. We measure it in terms of change in volume, right? The volume was here, right? That much. Now it's only this much. So a change in volume is more useful. And then the force is in terms of pressure. So pressure is force per unit area, right? So we're going to do a little math and try to create an equation that is more useful than just force times distance in terms of gases. So if pressure is equal to force per unit area, then we want to solve this for force, because that's this term right here. So if we solve it for force, we get pressure times area. Okay. Distance comes in this form. If we have this is a fixed area here, and it moves this distance, then the volume of that cylinder that it moved is distance times area, right? That's the volume of a cylinder. If you know the area, you know the height, then the volume, the change in volume, let's say, yeah, change in volume is equal to area times distance. Well, then we want to solve for distance here. Delta V over A is equal to distance. Now we can substitute this one in here and this one in here. And we get work equals P times A times delta V over A. And the A's cancel, numerator, denominator. So pressure times change in volume is an expression of, where is it? There it is. Pressure times change in volume is an expression of work. In reality, the pressure can change also. So we should say work is actually a change in pressure times volume if we let either one of them vary. Okay, there's a problem though. A change in volume is positive. In other words, we say final minus initial. So the final volume is this, and the before volume is this. So minus initial volume is equal to a change in volume. Well, what's the sign on that value? Initial was bigger than this one, so that's going to give us a negative value. But if we multiply that negative volume here times pressure, and if the pressure is constant, then let's use this one. If the pressure is constant and we make that one negative, then that makes W negative. Work was done on the system by the surroundings. So work should be positive. But by our calculation, W is negative. So what we have to do is fudge. Okay. We say W equals negative pressure times change in volume. And that corrects for the difference in expressions of volume and work. So now we come out with the correct expression relative to the system. That's why the negative is there. So look at what happens if we use units that we're familiar with. Pressure is in atmospheres, right? And volume is in liters for our example. So work is negative liter atmospheres. If you do that calculation, then how are you going to equate that to any other energy units? If you've got energy units from another part of the system in joules, you need to be able to convert those between the two. So that's what 1 liter atmosphere is equal to 101.3 joules. That's your conversion factor. And that should be, actually, that should be in useful information. Check this, sure. Let's see. There it is. Middle of the second column. 1 liter atmosphere is 101.3 joules. So you don't have to memorize it. Unless you just want to. Okay. So now we have a way of expressing work done on or by a gas. So which of the following performs more work? All right. If we take this gas is expanding against a pressure of 2 atmospheres from 1 liter to 4 liters, let's extract information from that word problem so that we can make sense of it. So what's the initial, let's see, pressure is constant at 2 atmospheres. What's the initial and the final volumes? The initial volume, if it's expanding from 1 liter to 4 liters, the initial volume is 1 liter and 4 liters. Okay? So work is going to be negative P delta V, and that's negative 2 atmospheres. And then final minus initial, or 4 minus 1 liter. So 3 times 2 is 6. We have minus 6 liter atmosphere is the amount of work that the gas did on its surroundings. So as an expanding gas does work on its surroundings. So during the power stroke in your engine, the cylinder is moving from top dead center down. It's expanding, and it's doing work by pushing on the connecting rods and causing your wheels to turn after it gets through the transmission, of course. So it has done 6 liter atmospheres of work in that example. In the second example, we have 3 atmospheres. So on this side, I'll put B. On this side, we have 3 atmospheres. And it's expanding from 1 liter to 3 liters. Okay, so we do the same calculation. Minus pressure, 3 atmospheres. And then final minus initial. Final 3 minus initial. That's 2 times 3 is minus 6 liter atmospheres. So the moral of this story is we've done the same amount of work, just under different conditions. All right. Now, I mentioned the balance between Q and W to determine the change in internal energy. So here we have our overriding equation is delta E equals Q plus W. And in the first example, we want to know what's the sign on delta E if, excuse me, if work is greater, if it's an endothermic process. An endothermic process means what? Okay, Q, W. So an endothermic process means we're adding energy, we're adding heat to the system. That means this has to be positive. Okay? And it performs work on its surroundings. So that would make the work negative. Okay? So if heat is less than work, or work is greater than heat, if heat is less than work, then that means the negative is greater than the positive, and delta E is negative. Okay? If work is less than heat, go the other way. Right? So if work is less than heat in absolute numerical terms, right? We're leaving out the sign for these things, right? Just the absolute values. The value here is greater than this one. This one's greater than that one, and this would be positive. Okay. Okay. For the next example, let's see, did I put those here? Yeah. So that's negative and that's positive. There we go. So if work is done, we still have an endothermic process. Let's see. No, now the process is exothermic. So Q in this case would be exothermic. And work is done on the gas by its surroundings. That's just positive. That's the change. Now, if work is greater than heat, if we do it this way, work is greater than heat, then we have positive is greater than negative, and delta E is positive. And if we go the other direction, if heat is greater than work, then the negative wins, and delta E is negative. Okay. Good. I don't know about the people at home. See if heads are spinning. It's a balancing act. All right, now we're going to talk about that term enthalpy that Professor Dave mentioned. Enthalpy is designated by a delta H. And it uses the same units of measure as Q, but they're different values. We can't say that delta H is equal to Q under all circumstances. Now I'm going to present a proof in a minute where there are certain conditions under which delta H and Q are identical. And those are the conditions that chemists like to use so that they can measure heat transfer and equate that to enthalpy. But it requires just the right conditions. Otherwise, they're completely different values. First of all, this is a path function. Heat transfer is a path function. This is a state function. Delta H, enthalpy, only matters how you got there. It doesn't matter how you got there, it just matters your current state. Right. Q is actually the amount of heat transferred to or from the system. It's a measured quantity between two different temperatures of the system and the surroundings. All right, and there's our equivalent to Q and W. Reminded the delta E again. All right. Delta H, on the other hand, think of it in terms of potential. This is measured heat transfer. This is potential. Potential heat. And in our cases, it's potential heat that's available in a chemical reaction. And it's defined by these terms. Delta H is equal to delta E plus any other changes. This work term, pressure times volume. Okay, that's how we define enthalpy. So what's the equivalence of delta E? Well, delta E is also Q plus W. Okay. What about this one though? What is it equal to? Well, if we let pressure remain constant, like we did with our previous example, then we bring the P outside, and now we only let the volume change. Okay. In this case, let's see. So far, so good. Oh, W equals, then W equals minus P delta V, if we're still letting the pressure remain constant. Okay. So if that's the case, then this term right here is equal to that term, minus P delta V plus P delta V and Q. So what we're saying is these two terms cancel out. As long as pressure is constant, then enthalpy is equal to heat. So those are the conditions. If you conduct an experiment under constant pressure and measure the heat transfers, then you can say the heat that you measured is equal to the enthalpy of that equation. Okay? That's the only condition under which enthalpy and Q are equal, numerically equal. All right. So let's say we're studying a process that goes from a one pressure, volume, and temperature to another pressure, volume, and temperature. There are many paths that we can take from one to the other, to these two thermodynamic states. In that case, Q and W will be a certain value for one set of P1, V1, T2 to P2, V2, T2. But if we change the values, then the Q and the W aren't necessarily equal. They won't be the same as they were before. However, it doesn't matter what we do to that pressure, volume, temperature, the enthalpy will always be the same. That's because it's a state function. Now, what we're leading up to is the usefulness of enthalpy over Q when we do our budgeting of energy transfers. So what we're saying is that if we know the enthalpy of the products and we know the enthalpy of the reactants, all we have to do is subtract the reactants from the products, and we can find out what the enthalpy change for that reaction is. All right. Just a reminder. Okay. So now we're getting to the point that we can actually solve problems stoichiometrically for a reaction. In this case, we've got propane, C3H8, plus oxygen yields carbon dioxide and water. And let me put that one up there. A different marker. C3H8 plus oxygen yields carbon dioxide plus water. I'm going to leave out the phases. 4. And we're told that the enthalpy for this reaction is minus 2221 kilojoules. Now that says kilojoules per mole of propane, which is true. But when you look these up, if you look up this reaction in a reference manual, and you're looking for the enthalpy for that reaction, it will simply say kilojoules. So this is an exothermic process, right? The negative value means that heat is being evolved. And the reason they leave per mole of propane off of it is because it depends. If you're interested in the transformation in terms of propane, then it is. It's that much heat per 1 mole of propane. But in this reaction, it's also that much heat in terms of 5 moles of oxygen, or 3 moles of carbon dioxide, or 4 moles of water produced. So you can use that, you can create, depending on what you need, you can create a value over here, kilojoules per 4 moles of water. but it only pertains to this reaction. So that's probably why they say per mole of propane, because without the propane, the rest of them don't mean much. Okay, what we want to do is find out if we have 5 grams of propane and excess oxygen, that means we're going to use up all the propane. How much energy do we get out of it? Okay. This is in terms of moles. So we have to convert grams to moles. Once we convert grams to moles, then we can say something about the conversion. And if we have 0.1134 moles of propane, then we can use minus 2221 kilojoule per mole of propane, and just multiply that times this, and we'll get the amount of heat that can be produced as minus 252 kilojoules. Uh, 5 grams of propane, that probably wouldn't even be enough to heat up your grill. You might get your grill hot to the touch, but it'll take a whole lot more than that. Okay, so that's an example of a stoichiometry using heat. Calorimetry, and I pull that from the back of your mind. When I talked about an isolated system where nothing crosses the boundary, matter doesn't cross, energy doesn't cross, that's our calorimeter. Calorimetry is the science of measuring heat. We're going to do that in the lab. We're going to measure heat transfer in a reaction, 3 different reactions actually. We're going to have an acid-base reaction. Put sulfuric acid and sodium hydroxide together and measure a change in temperature. And that will tell us how much heat was transferred. And I'll get to that in a second. Then we're going to measure the heat of solution. In other words, we're going to put sodium carbonate in water. And make it liquid, actually make it aqueous. And there's going to be heat. I'll give you a clue. There's going to be heat developed, and we use a delta for heat, evolved. And then we're also going to do sodium bicarbonate, sodium hydrogen carbonate. Put it in solution. It's going to absorb heat, so it should get colder. Temperature should drop. And we're going to measure those in the lab and then do calculations, of course. Now, we got to introduce some terms here before we can go any further. The one that I left out was just simply heat capacity. Heat capacity is the amount of heat that can be absorbed or evolved with a change of temperature. And it's an extensive property. That means if you have a larger amount, you get larger heat capacity. And this is the term that we're going to calculate first on that first sheet in our method next week, the heat capacity of our calorimeter. How much heat can the calorimeter absorb or evolve in the process? We need that correction factor. The others are going to be specific heat capacity. Specific heat capacity is an intensive property. In other words, it doesn't depend upon how much substance there is. And in words and prose, it's the amount of energy required to raise the temperature of 1 gram of a substance by 1 degree Celsius. So the amount of energy required to raise the temperature of 1 gram, 1 degree Celsius. That's the unit of measures. The heat required to raise the temperature of 1 gram, 1 degree Celsius. Okay, joules per gram degree C. That's specific heat capacity. We'll also be introduced to another one, molar heat capacity. Molar heat capacity simply substitutes for grams, it substitutes moles. Sometimes this one is more useful. Okay. We're going to use those values in an equation. I'll show you the equation in just a minute. Or Professor Dave might show it to you. See how we do it. We got till when? 350. Okay, we're good. We're going to have to bleed into lab time. Okay. So for our calorimeter, since it's an isolated system, anything that happens in Vegas stays in Vegas. In other words, whatever happens in that calorimeter in terms of heat transfer stays in the calorimeter. It doesn't exchange with the surroundings at all. So if the reaction absorbs heat, then the temperature is going to drop. And if the reaction produces heat, the temperature is going to go up. Okay, I guess I'll give the floor to Professor Dave.
Hey, it's Professor Dave. Let's talk about calorimetry.
He knows a lot about the science stuff. Professor Dave explains.
Different substances absorb heat at different rates due to various structural factors. The heat capacity of a substance is the amount of energy required to raise the temperature of that sample by 1 degree Celsius. A variation of this that is more useful for calculations is the specific heat of a substance, which is the energy required to raise 1 gram of a substance by 1 degree Celsius. Heat, temperature, and heat capacity are all related by the following equations. The amount of heat exchange in a reaction is equal to the heat capacity of the substance times the change in temperature for that substance. Or, more practically, the heat exchanged is equal to the specific heat of the substance times the grams of the substance present times the change in temperature. We can use this information to learn about heat transfer using a process called calorimetry. For those of you in an introductory chemistry course, you'll probably do some variation of a coffee cup calorimeter experiment. Let's look at how those work. A coffee cup is a pretty good insulator. That's why we use it for coffee, so that the heat doesn't escape so quickly and the coffee stays hot for longer. This makes it possible to take pretty reasonable data about the temperature change in a cup of water when we add a hot piece of metal. We can measure the temperature change in the water and use that information to calculate the specific heat of the metal. So, let's say you heat up a metal by placing it in boiling water at a known temperature until it is just as hot as the water. Then, with tongs, you place it in a coffee cup containing a known volume of room temperature water with a thermometer. The water in the cup will heat up slightly as the heat from the metal flows into the water, and we can record the resulting temperature change. From there, we just do some math. We use the specific heat equation and plug in the data for the water. The temperature change is what you recorded. The mass of water in grams is equal to the number of milliliters of water. And the specific heat of water is a known value. This allows us to calculate the heat absorbed by the water. Well, the heat absorbed by the water was the heat released by the metal. So we can take that same quantity of heat and plug it into a new equation for the metal. That value goes there. We weighed the metal beforehand, and this time the temperature change of the metal is from the boiling water to the final temperature in the coffee cup. so you can solve for the specific heat of the metal. This is useful for identifying unknown metals if you are given a few different specific heats and asked to decipher which metal you are given. Let's check comprehension. Thanks for watching, guys. Subscribe to my channel for more tutorials, and as always, feel free to email me, ProfessorDaveExplains@gmail.com.
It's not. The way Professor Dave described using that calorimeter is the way I was taught. But I've since learned that there's a better way. It's more useful, it's more flexible, and I'm going to get to it in just a minute. So this is our calorimeter. It's actually 2 coffee cups, 8.5 ounce coffee cups. You slide one inside the other, just to add insulation. And then you have a lid and a thermometer. It used to have a stirrer in it, like that green thing. But the stirrer that I was using wouldn't stand up against certain chemical reactions, so we don't use it anymore. So it's not even there. I just use the thermometer, and if you move the thermometer around, it'll mix it. So this is an isolated system. Therefore, all the heat changes, everything that happens in that calorimeter is equal to 0. And here's what I mean by that. Let's see. There we go. That is, any heat changes that we can assign to, say, the heat change of what happens to the water. Or in the example that Professor Dave gave us, the heat change of the metal. And then we could also account for the heat change of the calorimeter. Okay. All of that added together must be 0. It has to be 0 because our system is isolated. And you can have as many terms as you want out here. Fewer is better. So it depends on what you're looking at. For the heat change for the water, we use that equation. This Q, well, actually Q is equal to the specific heat of water times the mass of the water times the change in its temperature, right? That's this term. And you also get the heat capacity for the metal times the mass of the metal, this is water, and the mass of the metal, and the change in temperature of the metal. And then if we introduce the calorimeter, doesn't use this equation. It uses a calorimeter constant that we determine independently times a change in temperature for the calorimeter. All right, so those 3 terms in this example all have to be equal to 0. Now, we know what this is for water. We measured the mass of the water. We measured the change in the water temperature before and after. And we know the temperature of the metal before it goes in, and its final temperature is the same as the water. And once it equilibrates, it's the same. We know the mass of the metal because we measured it, and this is an unknown. So we're solving for this one in this example. We measured this one earlier by a separate experiment. So we know what that one is. And the change in the calorimeter temperature is the same as it is for the water. Okay, so here we have an equation and one unknown we can solve for it. All right. Units of measure. So if we were to take this Q equals SM delta T, just look at the units of measure. What are the unit measure here? Well, grams. Measure temperature here, degree C. What are the units here? Joules per gram, degree C. Numerator, denominator. Cancel, cancel. Joules. So that's a good equation based upon our dimensional analysis. This one is only going to be degree C here. This is going to be joules per degree C. We don't have the mass term here because this is an extensive property. It changes with the mass of the calorimeter. We had a bigger, say if we use 12-ounce cups instead of 8.5-ounce cups, it would be probably a larger value. Okay. So that's how we do calorimetry. Now let's see, this first one is kind of intuitive. And then we'll get to calculations. So if we have a 100-gram sample of water at 90 degrees, and we add a 100-gram sample of water at 10 degrees, what should be the temperature? We've got equal amounts of water, which have exactly the same specific heat capacity. So they should meet in the middle. Right? So 90 plus 10 is 100 divided by 2 is 50. Should be 50 degrees. On the other hand, suppose we have water. In this case, we have 100 grams of water at the higher temperature, but we have 500 grams at the lower temperature. So it's a balancing act, and the larger number of grams of water will give us a temperature that's between 10 and 15. And we could actually calculate what that would be. Oh, I guess we are going to do it. Okay. So in this case, we know that the heat of the hot water and the heat of the cold water added together equals 0. And we can only do that if we also pay attention to the signs. Right? Some of those terms are going to be negative signs, some of them are going to be positive signs. That gives us an outcome of 0. So for the first one, we have S is the same for both of them. Mass is going to be different. Change in temperature is going to be different. Right? So for the first one, we have the S is the same. We have a 100-gram sample for the hot one. Yeah, for the hot one. And the final temperature is going to be our unknown. Whatever the temperature is when they meet in the middle. It starts off at 90 degrees. That's the initial temperature. Whenever we see a delta, this is your starting position. Whenever you see a delta something, a delta X, always think X final minus X initial. Final minus initial. That keeps your signs. So if the initial is higher than the final, then it's going to be a negative value. So we have, say, there's the cold one, and the hot one is a change in 500 grams. The same final temperature, but a different beginning temperature. And then it's just a matter of solving that equation and solving for the unknown. So we end up with an answer of 23 degrees. So were we right? We thought it would be between 10 and 50, yeah. So it's correct, 23 degrees. Okay, in this case, we've got water and an iron ball. Now we've got two different specific heats, but it's the same process as before. We're ignoring the calorimeter for the moment, actually. And if we set it up to find the final temperature, we set it up similarly, only now the value for the specific heat of iron is lower than water. It's about 1/10 of what it is for water. So that's why water can absorb a lot of heat before it changes phase. Okay, so our temperature is going to be 18 degrees based on that calculation. All right, this is where I would pause for if we didn't have the time. Say if we were on Thursday, I'd pause it here. It would pick it up on Tuesday, but since we've got time, moving on. Okay, this principle of enthalpy, where it doesn't matter how you got there, is used in this law called Hess's law. Hess's law allows us to calculate the enthalpy of an unknown or an uninvestigated reaction based upon knowing two or more other reactions and what their enthalpies are. Because we can add them together, we can subtract them, add them, multiply them, do whatever we want to make the component equations add up to the target equation and then calculate the enthalpy from that. That's based upon Hess's law. In other words, it's not necessary to conduct the calorimetry in a laboratory if you know the enthalpy of the component reactions. You can predict the enthalpy of an unknown reaction. And that's also valuable if the reaction is suspected of being extremely exothermic, like nitroglycerin. Oh, Dave's going to talk about Hess's law. Oops. Sorry.
Professor Dave here. I want to tell you about Hess's law.
He knows a lot about the science stuff. Professor Dave explains.
Thermochemical equations can be manipulated to give important data about chemical reactions. We can use them to predict exactly how much energy will be absorbed or released by a reaction, which is very important because we don't want any unexpected explosions. There are two ways we can use tabulated thermochemical data to calculate the delta H of any reaction. The first way requires that we manipulate thermochemical equations in specific ways. So let's be aware of some rules. First, if a reaction has a particular delta H, the reverse of the reaction will have the opposite delta H or the same number with reversed sign. Second, if molar quantities in the equation are multiplied by a coefficient, so is the delta H. So if you double all the substances, double the delta H. These are things we can do to thermochemical data to be able to add equations together to result in a reaction we are curious about. Here's what I mean. Let's say we want to know about the change in enthalpy associated with a reaction, like this one. But it is difficult to measure experimentally. We can take other reactions with known enthalpy changes and rearrange them to align with our equation and get the data we want. The first reaction provided has carbon graphite on the left, which is where we want it. But the equation we want has 2 moles of graphite, so let's double this one. We get 2 moles of everything instead of 1, and we double the delta H. Next, this other one has CO on the right, where we want it, and in the right amount. So all we need to do is add these equations together. The O2 and CO2 will cancel because they are present in the same amounts on both sides, and we are left with the substances in our original equation. Since we added the equations, we also add the delta H's to get the delta H for our equation. This kind of manipulation is allowed by Hess's law. We can manipulate the coefficients of a reaction or reverse its direction in any way necessary as long as we change the delta H associated with it in the appropriate way. Then we add or subtract the equations as necessary to give us precisely the equation in question. The delta H you get by doing the arithmetic will be the delta H for the reaction. Another way to calculate an unknown delta H is to use standard enthalpies of formation. This is denoted by the following symbol, and it represents the enthalpy associated with forming 1 mole of a substance from its respective elements in their standard and most stable state. Most stable state means the most common allotrope or physical form of an element. So carbon graphite instead of diamond, diatomic oxygen instead of ozone, and so forth. Standard state just refers to standard temperature and pressure, which is room temperature and atmospheric pressure at sea level. That's what is meant by the degree symbol. We can calculate the change in enthalpy for a reaction by adding up the standard heats of formation of the products and then subtracting the sum of the standard heats of formation of the reactants. The heats of formation can be found in your textbook or online, and you just plug them in, multiplying each value by the coefficients in the balanced equation. Let's check comprehension. Thanks for watching, guys. Subscribe to my channel for more tutorials, and as always, feel free to email me, ProfessorDaveExplains@gmail.com.
Of course, he introduced some concepts. Let's go back to the first one where we add equations together to get our target equation. In this case, we've got an example of nitrogen plus oxygen yields nitrogen dioxide. And this is a balanced equation with 68 kilojoules as the enthalpy for that equation. Now we're going to say, all right, can we combine a second and a third equation here to get that first equation and determine the same enthalpy. So does delta H1 equal delta H2 plus delta H3? Well, it depends, right? In this case, we didn't have to do anything to the equations. We didn't have to multiply them by anything. We didn't have to flip them. So the nitrogen monoxide cancels on both sides and leaves us with the target equation right here. So we just add those two values together and we get 68 kilojoules. This is an endothermic process because the delta H is positive. That was an easy one. And this is an energy diagram interpretation. On the right would be the reaction as written. And on the left would be the two-step reaction to get to the one on the right. We end up in exactly the same place with exactly the same amount of energy produced or absorbed. All right, we have to watch our rules, though. If we have to reverse a component equation to get our reactants and products on the correct side, then we change the sign of the enthalpy. If we also have to multiply by a factor, remember, once an equation is balanced, you can multiply it by any factor and you haven't changed the ratios. So that's permitted. But when you do that, you also have to multiply times the enthalpy, because the enthalpy in this case is an extensive property. In other words, you get more enthalpy if you have more reactants. Okay, sometimes you have to flip and multiply. Okay, here we have two equations, and notice we've got fractional coefficients. So don't let that bother you. It's permitted. It's just we learned initially to go for the lowest whole number multiples. So if we have these two equations, can we produce that final equation from those two? Well, if we look at what's available, let's see, we need ammonia. There's ammonia in that one. We need oxygen. There's oxygen in the second equation. We need water in the second equation, nitrogen in the first equation. So we have all the components there that we need. We just have to arrange it so that we can add it together. And when you add it together, the two equations as modified, they have to equal the target equation. Otherwise, the enthalpy calculation is invalid. Okay, working backwards seems to be the best approach. Working backwards from, what we mean is work backwards from the target equation and then go to your component equations and pick the ones that fit. Because you may say, for instance, you've got a sneaky instructor, and he gives you a list of 10 equations, but you may only need 3 of them. You go to your target equation, that tells you which ones you're looking for. Then we reverse any equations that need to flip the reactants and products and multiply wherever is necessary to get the right coefficients. Okay, so in this case, we had to reverse the reactions in order to put ammonia on the right-hand side where it is in the target equation. And we didn't have to flip the second equation because it already had water where it needed to be and oxygen where it needed to be. But we will need to multiply. Right, the first one we need to multiply by 4 in order to give us 2 nitrogens that are in the target equation. And the second one we need to multiply by 3 to give us 6 waters. And of course, we have to use those multipliers for the enthalpies as well. Right, so there's the result in the top. There's the result of all the manipulations we've done. And can we add those two together and get the final equation? Well, if we cancel the hydrogens, which are one on one side, one on the other, and then add them together, yeah. Notice we've got 2 nitrogens plus 6 waters on the left. That's good. 4 ammonias and 3 oxygens on the right. We're good. So that means since we have also applied the correct corrections to the enthalpies, now we can add them together. And this reaction is extremely endothermic. 1268 kilojoules. And that's 1268 kilojoules per 2 moles of nitrogen, or per 6 moles of water. Whatever you need. All right. Now we're at the point where we can also use heats of formation. So when we're writing the heats of formation for something like, let's say we want a heat of formation for the compound water. In its most stable, common form at room temperature and pressure, it will be a liquid. Now we form that from its elements in their most common stable form. So that would be hydrogen, like that, and it's a gas at room temperature and pressure. And oxygen would also be a gas. Now, once you've got 1 mole of your product, you don't touch this side. That's why we have to use fractional coefficients. We need 1 mole of oxygen. So that means we need a half of that one. We need 2 moles of hydrogen. We got it. So this would be expressing the heat of formation of water, all we have to do now is insert the enthalpy for that, whatever that happens to be. And you can use these now because enthalpies are state functions. You can use these to calculate the enthalpy for a reaction if you know the heats of formation for all the compounds in the reactants and products. Now, if there are any elements in the reactants and products, you ignore them because by definition, they're zero. Okay. Let's see. For a compound, for a gas, the standard pressure is 1 atmosphere. If you happen to have a solution involved, 1 molar concentration. If it's a pure substance, it'll either be a liquid or a solid. And then for elements, 1 atmosphere and 25 degrees C would be standard conditions. Even if it's a gas. The only time we had 0 degrees Celsius as a standard temperature was when we were exclusively working with physical laws of gases. Every other time is 25 degrees. This is just an illustration of what's happening. We take the reactants in step 1. How much energy does it take to break the bonds? Right, 75 kilojoules for methane, 0 kilojoules for oxygen because that's the standard. That's like the ground floor. And then we get the elements, and then when you put the elements back together to get the compounds, you get a certain amount of energy back. And when you add all those together, you get the minus 891 kilojoules as the product. Okay, so this is what it looks like in mathematical forms. The standard enthalpy for this reaction is equal to the summation of the standard enthalpies of formation for products minus the summation of the standard enthalpies of formation for the reactants. We put these ends in here because the standard enthalpy of formation is always based upon 1 mole. So if you have 2 moles or 3 moles, you have to use that multiplier. And for this example, notice that sodium plus water yields sodium hydroxide plus hydrogen gas. Sodium is in its standard state, hydrogen gas is in its standard state, so those values are 0. So we only have to be concerned with 2 moles of sodium hydroxide at minus 470 and 2 moles of water at minus 286. So 2 times that and 2 times the other one. And you take the final here, minus 470 times 2, minus 286, which would be a plus times 2. And when you add those together, you should get minus 368 kilojoules. So this is an exothermic process, and that's what I've observed. When you add a piece of sodium to water, you get a violent exothermic reaction. In fact, it'll be so violent that it'll produce that hydrogen gas, and the hydrogen gas will come bubbling out of the water. And there's enough heat generated in the process, it will ignite that gas. So you have a hydrogen flame on the surface of the water where the hydrogen's coming out. It's even more spectacular with potassium. Potassium is more reactive than sodium in water. So if you want to, if your neighbor's dog won't shut up at 2 a.m. in the morning, and they got a swimming pool, you just take a nice big chunk of sodium or potassium and throw it in their pool, and it'll crack the bottom. It produces so much violent reaction. I didn't tell you to do that, though. All right, for the last part of the discussion, we're going to generalize. since we're talking about thermochemistry, we naturally are interested in chemistry in terms of energy production. How do we produce energy in this country? Well, when the settlers first arrived, most of the energy was produced from wood because there was lots of wood. I mean, it was said that you could land on the shore in Carolinas and climb a tree and stay in the tops of the trees all the way past the Mississippi River until you get to the Great Plains. And you'd never have to touch the ground. It was that thick. But of course, over the centuries, we've chopped all the trees down. And a lot of that was to produce arable land. Remove all the trees and the stumps, and then you can till the soil and grow crops. And in the Northeast, the trees, especially the maples and the oaks, were cut down to make ships. They built ships up there. In fact, all of the slave ships that were built in this country were built in New England. And then they went across to, let's see, where did they go from there? They went to England, and then England took them. They went down to Africa and picked up the slaves, came across primarily to South America and the Caribbean and dumped most of them off and picked up in payments, their payments, and then they bought molasses or sugar and took it back to Europe. And it was just a vicious cycle. Most of the slaves that entered the New World, their ancestors are found in, their descendants are found in South America and the Caribbean. We got just a tiny fraction of them in this country. We had a war over it though, and they didn't. Okay, so then we graduated to fossil fuels. In fact, fossil fuels were first used in England and Western Europe and Eastern Europe in terms of coal primarily, peat and coal. And then once oil and natural gas were discovered, they started to replace coal for lots of things because it was easier to get them out of the ground than go down there and dig it out. You just sink a well and there you go. And then when technology advanced far enough, we were able to produce, well, and once electricity was, Westinghouse and Nikola Tesla showed how to transmit electrical power great distances, then these large power plants, whether they were petroleum-based, fossil fuel-based, or hydroelectric, then we could use those to generate power from a source and send it everywhere. That's another discussion. The problem with hydroelectric power is that there are only a few places where you can build large enough facilities, large enough dams and dynamos to produce electricity economically. And then once you built the dam, they begin to silt in. In other words, when water's moving fast, it carries a heavier silt load easily downstream. When it slows down behind a dam, it drops that silt. So the bottom of the lake starts to build up like that. And it just depends on how much the silt load is as to how long you can go before you have to dredge. In this country, it's not too bad, but we have used, we've dammed every river that is economically feasible for large power plants. Now you can still dam up small streams and produce electricity for 2 or 3 or 4, 10 houses. But large projects, we've used it all up. There's no other place that we can build dams anymore. Talking about the silt load, the Aswan High Dam that was built in Egypt on the Nile River by the Russians, it took a matter of 10 years and it was silted in because the Nile carries such a huge silt load that when they built that dam, it just started filling up. And they didn't have any choice but to either dredge it or blast it. Nuclear power. Nuclear power, in my opinion, is the solution to our power problems. And to placate the global warming alarmists. Right. The problem of global warming is not man-made. That's my stance. But even if it were, nuclear power would be the way to go because it produces no greenhouse gases. All it produces is waste heat. And we have a virtually unlimited supply of fuel in this country. We don't have to get it from anybody else. So nuclear power is, in my opinion, the way to go. It's just how do we get there safely? And technologies have really improved over the past decades since nuclear power fell out of favor with 3 Mile Island and some other disasters. So that's where I'd go. I'd go nuclear. Notice in this list, wind and solar were missing. And that's primarily because they're both unreliable and they're insignificant to the total output of energy. In other words, to produce the amount of energy we need right now, you'd have to cover half the country with solar panels or wind turbines. And we don't have a way to store the energy efficiently. That's a problem. So when the sun goes down or the wind stops blowing, what do? It's not what they call a base load. Those are not base load technologies. Base load technologies are like coal-fired power plants, nuclear, even hydroelectric can be turned on and off like that. So it's good as a supplement. And this is just a history. Notice we started off with wood and then gradually moved to petroleum and natural gas over the centuries, over the decades. Talk about the Earth's atmosphere, right? It transmits visible light from the sun very efficiently. It's not absorbed. In the upper atmosphere, ultraviolet light is absorbed primarily by ozone. And ozone is produced by that ultraviolet light. So it's it shoots itself in the foot. Ultraviolet light causes oxygen in the upper atmosphere to add an oxygen atom to it. And then it becomes even more efficient at absorbing ultraviolet light. So, and it has a limited life and it decomposes and then has to be recreated. But when this visible light penetrates the Earth's atmosphere and strikes the surface, some of it is used if it's absorbed by plants. Some of it is reflected, and usually it's reflected in longer wavelengths. So if it comes in as blue light, it'll go out as red. Or if it comes in as orange, it'll go out as infrared. And that's where the global warming idea comes from, because the molecules in the Earth's atmosphere that will absorb light absorb in the infrared. So we re-radiate in the infrared, and carbon dioxide, water, methane, some other molecules absorb that energy and keep it in the Earth's lower atmosphere. Carbon dioxide is moderately absorbing. Methane is much more efficient at absorbing. Water is less efficient than carbon dioxide at absorbing infrared light, but there's so much more of it. It just overwhelms any of the others. Water is the primary infrared absorber in the atmosphere. Okay, so this is the idea behind global warming I just described. Now, new energy sources. All right, I mentioned nuclear. We can convert coal into gas, natural gas, and that leaves behind a waste product that we don't have to spew into the atmosphere. And there are technologies that take advantage of that, those products. Hydrogen fuel economy is the holy grail, because when you burn hydrogen in the atmosphere, it produces water, nothing else. Or you can run it through a fuel cell and produce electricity directly. And that would be great for, if you want an electric vehicle economy, you need hydrogen and fuel cells, because you can stop and fill up your hydrogen tank as quickly as you can fill up gasoline, be on your way. You don't have to charge batteries. Other alternatives, oil shale, which was made more available by fracking. Natural gas, more available by fracking. We don't have time to go into the details there. Ethanol can be produced as a fuel, and now most gases have about 10%. You pull up to the pump, it says contains up to 10% ethanol. Mixed in with the gasoline. The problem with ethanol is if it's made from grain, like corn, it costs more to produce it than you get back in energy. It costs more energy to produce a gallon of ethanol from grain than it does the energy you get back from burning it. So if it weren't for government subsidies, ethanol industry would go in a day. It would be gone. Methanol is another possibility. Seed oils. Solar, they have numerous problems. Solar, photovoltaic and wind. Intermittent availability, I mentioned that one earlier. Ineffective storage technologies. We just don't have the battery storage capacity or technologies that efficiently store large amounts to take us over the non-available times. And they're uncompetitive economically. Without government subsidies, solar sources would go out also overnight. And then there are environmental hazards that the proponents of solar energy seem to ignore. They don't publicize them. They produce lots of hazardous waste just to make the batteries or the solar panels, or the armatures that go in your wind turbines. And that discounts the fact that most of the rare earth metals that are required for those technologies come from China, our sworn enemy. And then they only have a limited life, and you got to get rid of that waste. So they produce more hazardous waste than any other technologies. And then there's nuclear. That's the solution to our immediate problems. And we're done.